of my own. So one of the organizations on campus, the Alpha Eta Alpha, which is one of the pre-health societies, I can't keep them all straight, but this is one of them. They have a general meeting tomorrow, 6:30 to 8 p.m. I think this is the pre-health organization that caters towards all majors, not just science majors, so it's an opportunity if you want to go check that out. And then my department chair, who's the closest thing that I have to a boss, why is this so small today? Hang on, I'm going to get out of here and try this again. Oh boy. Again. A request from my department chair, who, as I said, is the closest thing I have to a boss. He wanted me to let you all know that the chem labs are offered over the summer sessions, in case you weren't aware of that. So many students in here tried to take chem lab this semester and were blocked out because of the limited enrollment. So if you want to get caught up, they are available in the summer. They tend to not fill up at all or as fast in the summer, so it's a lot easier to get a spot during the summer. And especially if you were worried about that 1 credit hour chem lab screwing up your semester, your schedule for next fall, you can get it out of the way in the summer and it'll be over with. The lab meets, I think, 4 days a week for like 2 hours, so it's pretty condensed. It's a almost everyday commitment, but you get through the whole lab in about a 4-week or 5-week period, and a lot of students like that option, especially for the labs. All right, so both of the general chemistry labs are in the summer if you're interested in those. All right, but let's get on then to the chemistry today. So what we're going to do today is we're going to finish Chapter 6, which we kind of I've gotten mostly through it, but we're talking now about solution stoichiometry. So we've talked a lot about different types of chemical reactions that happen in solution, and now we're dealing with the aspects of those related to moles and converting moles into different amounts and things of that. So we talked about last time how the key difference here is that we're using molarity as a conversion factor to go between volume and number of moles, and we're going to do that here as well. And so just like we have for regular stoichiometry problems, there's also the possibility of having to determine what the limiting reactant is. So if we mix two solutions together and we know the amounts of both solutions that we're using, we have to, before determining something about how much of the product forms, we have to figure out what the limiting reactant is. And that's what this problem does here. So we're going to mix together 125 milliliters of 0.25 molar sodium sulfide with 95 milliliters of 0.45 molar lead nitrate. We want to know what the mass of the precipitate that forms is. So just like any stoichiometry problem, we have to start with a balanced chemical equation, and for many of the aqueous reactions that we talk about, precipitation reactions and acid-base reactions, and especially, you're going to have to be able to come up with the form of the balanced chemical equation on your own. And so for this one, we have two ionic compounds that we're combining, so we should think of this obviously as being a precipitate. Oh, geez. It still wants me to zoom in, that's why. Or zoom out. All right, we're back in business. So the first thing we have to do is write the balanced chemical equation. So we're combining two ionic compounds, so we should think of this as an ion exchange or precipitation reaction. So we have aqueous sodium sulfate. We're told that they're solutions, so we don't have to worry about their solubility for the reactants. And then, as we said, when you do these ion exchange precipitation reactions, we just swap the cations and the anions with each other. So sodium is going to pair with nitrate to make sodium nitrate. It's a +1, -1 ionic compound, so just one of each. And then lead, which is in the +2 charge or +2 oxidation state, is going to combine with sulfide 2- and get PbS. And this one's going to be our precipitate. So just about all sulfide compounds are insoluble outside of the group 1 alkali metal sulfides, and lead is another one where it's almost always insoluble. So pretty obviously this is our solid precipitate that forms lead sulfide. We have to put a 2 there to balance it. I think that's the only coefficient we need. So the key point here is that the two reactants combine in a 1-to-1 ratio, and they're going to then form 1 mole of our of our precipitate lead sulfide. So we write the balanced equation. The next thing we have to do is determine the limiting reactant. And just like we have for the normal types of stoichiometry problems we did in Chapter 5, there's a few different ways we could do this. The way that I like to do it is what I call the stoichiometric ratio method, where we're going to find, for each reactant, we're going to find the number of moles, and then we're going to divide that number by the coefficient, and the smaller of those two ratios is going to be what identifies the limiting reactant. All right, so for both reactions, we're going to find the moles. We have sodium sulfide, and the only difference here is before we would typically use the mass of the compound to tell us how many moles there are, using molar mass as the conversion factor. Here we're going to use volume and molarity, and so we have 125 milliliters of the sodium sulfide solution. And then the molarity is 0.250 molar. Remember that capital M means moles per liter. And so we use that as a conversion factor, 0.250 moles of sodium sulfide. And we can shortcut this as per 1,000 milliliters. Molarity is per liter or 1,000 milliliters. Those are equivalent. And so that converts milliliters of solution into moles. And that's the only conversion, that's the only step we have to do. So it's 0.0312 moles of sodium sulfide. Now remember that the number of moles by itself doesn't allow you to identify a limiting reactant. You have to take this number and divide it by the coefficient. So we take that number 0.0312, and then the coefficient in the balanced chemical equation is just a 1 for sodium sulfide. There's no coefficient in front of it, so it's 1, and so that number is the same then. But if there were a coefficient other than 1, we'd have to divide those two. And we do the same thing for the other reactant, which is lead nitrate. So again, the amount of lead nitrate that we have is given to us as an aqueous solution with a volume and a molarity. So we'll use the same type of calculation to determine the number of moles of lead nitrate. We have 95.0 milliliters of that solution. And its molarity is 0.45. And that's again moles per 1,000 milliliters is a way to write that. And so what we get for the moles of lead nitrate is 0.0428. And then the stoichiometric ratio is just that number divided by the coefficient, which is also 1. So both of our reactions have a coefficient of 1, so the stoichiometric ratio is just the same number as the number of moles. So the one that is the smaller of these two numbers, 0.0428, 0.312, is going to be the limiting reactant. So this number is smaller, so we've identified that sodium sulfide is the limiting reactant. And then once we know what the limiting reactant is, whatever calculation the problem is asking us to do, we can go ahead and just use that amount of limiting reactant as our starting point. So the last step then is going to be just to calculate what the problem is asking for, which is the mass of the precipitate that forms. Alright, so let's rewrite the balanced equation just so we have it. So it's again a 1-to-1 reaction between sodium sulfide and lead nitrate. To form sodium nitrate, 2 equivalents, but those are our spectator ions, those remain in solution. And then our precipitate is lead sulfide, PBS, solid. And so our goal in this problem is to calculate the mass of this product that forms. And so we have to start with the limiting reactant. And so the mass of lead sulfide that forms, as we often do for limiting reactant problems, we can just start directly with the number of moles of limiting reactant. We had to calculate that anyway in the previous step to identify it as limiting reactant. So let's just start with that number. It removes a step from this calculation here. So we have 0.0312 moles of sodium sulfide. We determined that previously from the molarity and volume. Then we use coefficients from the balanced chemical equation to convert moles of sodium sulfide into moles of the product we're interested in, which is lead sulfide. Those are also a 1-to-1 ratio. So 1 mole of PBS forms for every 1 mole of sodium sulfide that reacts. And then finally, this is looking for the mass of the precipitate that forms, so we use the molar mass to convert from moles back into grams. So the molar mass of lead sulfide I gave to you here is 239.3. So 239.3 grams of lead sulfide, lead 2 sulfide, for every 1 mole. And so for this step, it's essentially the same type of stoichiometry problem we've always done, just converting moles of one substance into moles of another, and then once you have the moles of the product, you convert it back into a mass amount, and that gives us 7.47 grams. Okay, so that's just another example of a solution stoichiometry problem. Question? Yeah. Well, yeah, you determine the charges don't change, so you have to know what the charges of each ion are to be able to pair them up in the correct ratio. So sodium is always a +1 cation, right? And so when sodium pairs with nitrate, which is -1, it's going to be NaNO3, one of each. And then lead here is +2 because it has, I think I wrote that wrong. That should be NO3 taken twice. Hope I didn't make that mistake twice. Nope. Okay. So anyway, there's 2 nitrates paired with lead, so lead is +2, which means on the product side, lead would also be +2. Sulfide is -2, so that's why the correct formula for that is PBS. So you have to know how to determine formulas for ionic compounds, but keep in mind, when you're doing a precipitation reaction, the charges of the ions never change. If we were doing a redox reaction, they could, but in the precipitation reaction, you just keep the ions exactly as they are as reactants, and just make sure when you pair them up as products, you swap the cation and the anion with each other, and then you pair them in the correct ratio to still balance whatever those charges are. So that's a good point, but yeah, when you predict the products of those, you have to keep in mind what the charges of the individual ions are to be able to write those correctly. Okay, any other questions on that? Alright, now the other type of solution stoichiometry problem we're going to do is referred to as titration, which is a word that often brings small amounts of fear into the eyes of general chemistry students. But I want to emphasize that titration is nothing bad or nothing to be scared of. It's just another type of solution stoichiometry where we're using, again, molarities and volumes primarily to determine number of moles of substances. But we should define what titration is. How is it a little bit different than what we've been doing? So what you do in a titration experimentally is you're using a solution of known concentration. So you have a solution where you know what its molarity is. And then you're going to add this solution to another solution that it reacts with where you don't know the concentration. So you're adding a solution of known concentration, and you're using that to determine an unknown concentration. Alright, so one of the solutions, you're mixing 2 solutions together, they react with each other in some way. One of the solutions you know what the concentration is, one of the solutions you don't know, and by measuring how much of those you have to mix with each other, you can determine what your unknown concentration is, or something else about that unknown compound. Okay? So the most common type of titration, which I think 99 or maybe even 100% of the test questions will be, is acid-base titrations. So we're mixing an acid and a base. We know how those 2 things react with each other. And so what you do in an acid-base titration is you add a solution of a base to an acid or vice versa. Alright, so you do that, and then you add the base to the acid or the acid to the base until you get to what's called the equivalence point, or the end point. And so that's the point where the moles of hydroxide that you've added, if you're adding the base to the acid, or the moles of H plus that you've added if you're adding the acid to the base, so the amount that you've added equals the moles of H plus or OH minus, depending on which direction you're doing the titration, that were initially present. All right, and as we already learned in this course, when you do an acid-base reaction, the net ionic equation is always the same. It's H plus OH minus going to water, the recombination of H plus and OH minus to make water. And so the equivalence or endpoint of a titration is the point at which you've added exactly equal amounts of H plus and OH minus in terms of the number of moles. So the moles of H plus and mole of OH minus that you have in solution would be equal at that point, and they would have completely reacted with each other. If you do this in the lab, which you probably will at some point, again, I have a very poor knowledge of what happens in those labs, but I should learn better. But if you do this in the lab, which I'm sure you will because every general chemistry student has to do a titration, it's a law. If it's not really a law, man, you guys are dead today. So if you do it in the lab, how do you know when you've gotten to the equivalence point, right? Because like I said, you don't know the concentration of one of your solutions. Most acid and base solutions are just colorless liquids that look like water. You can mix them together in any ratio you want, and they're going to still look like colorless liquids. So the way that you do this is with an indicator. So the indicator is a little extra thing that you add to the solution that changes color once you get to the end point. And the reason why that happens, we're not going to worry about in this course. We'll deal with that in chemistry too. But if you want to just think of this as a black box or a magic substance that just changes color at the end point. So you can kind of see that in this picture here. You see that most of the solution is clear and colorless, but there's a little bit of a pink there. That's the indicator changing color as you add the base to the acid. And once you've added enough base to completely react with the acid, the entire solution will look pink. And that's the common indicator that's used for acid bases. There's other indicators that work in using similar principles. So they change colors at the endpoint, so that's how you know when you've gotten to that magic endpoint. Now, since this is a lecture course, not a lab course, we're not actually going to be doing titrations, but we want to learn how to use titration data to answer certain types of questions about solutions of primarily acids and bases. So one variation would be if we have a situation where we know the concentrations of both solutions, which often experimentally we don't, but let's say we know the concentrations of the base solution, which is sodium hydroxide, and the concentration of the acid solution. We want to know how many milliliters of the 0.126 molar sodium hydroxide solution are needed to neutralize 52.3 milliliters of 0.297 molar H2SO4. So this problem is, in some sense, a titration problem. You're adding a base to an acid, but here it's really just a standard stoichiometry problem because we just want to know how much of this base, one of our reactants, do we have to add to completely react with the other reactant, which is the acid. And so it just becomes a solution stoichiometry problem where, again, we're using molarity as a conversion factor to give us moles. So anytime you're doing a titration problem, you want to start with the balanced chemical equation. Now, the nice thing about titrations is that what you really need to have correct is the reactant side. Because whenever we're doing a titration, we're mixing together two reactants, and we're using that information to tell us something about one of the reactants that we don't know. So you don't really care what the products are in a titration type of situation. All we're going to do here is mix an acid with a base, and the amount of acid that we add has to be equal to the amount of base that we add in terms of the moles of each. And so you don't really have to even know anything about the products. It's so good to be able to write the full balanced equation, but you don't really care about the products in this particular type of problem. So anyway, when we write the equation, though, we have sodium hydroxide, which is NaOH, and then sulfuric acid, H2SO4. I gave you the formula of that, so you don't have to remember that that's sulfuric acid. So aqueous solutions of both of those. And like I said, we don't really care about the products for a titration problem because we're just interested in the ratio of the acid and base and how they react with each other. But if we want to write the products, remember that the products of a acid-base reaction are always an ionic compound in water, so we would form sodium sulfate and then water. So those are the products, and we have to have some coefficients here. The only coefficients that really matter are the ones that are on the reactant side. So what we see is that our base has one hydroxide, one OH minus. Our acid has two H pluses. Those two have to react with each other in equal amounts, so we're going to have two equivalents of our base to react completely with the two H pluses that are in our acid. So the important part is that these react in a 2-to-1 ratio, 2 moles of OH minus required to react with the 2 moles of H plus that this already has. That would also give us a coefficient of 2 in front of H2O, although we don't care about that for this problem. Okay? So that's the balanced equation. It's the left side of the equation that's the most important, the ratio of acid and base. And once we have that written out correctly, or at least once we know what the ratio is, which for acid-base problems is usually 1-to-1, 1-to-2, or at worst 1-to-3 or 2-to-3. I mean, they're usually going to be really small ratios, but you have to have that ratio correct before you start. Now we can just go ahead and solve the problem. So we're looking for the volume of NaOH solution that's required to neutralize this solution of sulfuric acid. So the amount that we know is that we're using 52.3 milliliters of our sulfuric acid solution. We can convert that into moles. We're doing stoichiometry here, so converting into moles is always a good thing. So we use the molarity of sulfuric acid, 0.297 per 1,000 milliliters. So it's 0.297 moles per 1,000 milliliters of solution. All right, so now we have moles of H2SO4. We're looking for the volume of our sodium hydroxide solution. We have the molarity. We know that molarity and volume are related by number of moles. So we can first find the number of moles of sodium hydroxide that we have to add to neutralize the solution. And so for that we use the coefficients from the balanced equation. So if we have this many moles of sulfuric acid, we have a 2-to-1 mole ratio. 2 moles of NaOH are required for each mole of H2SO4. So now we know how many moles of NaOH there are. And then the last thing we're going to do, which we haven't done yet, is we're looking for the volume of NaOH. We now have converted into moles of NaOH. We have the molarity, so we're going to use the molarity as a conversion factor to go back into volume. So it's going to essentially be the reverse of what we did in the first one. So we know from this molarity, 0.126, that for every 1,000 milliliters of NaOH solution, that's going to contain 0.126 moles. So we could have done this as 2 steps. We could have solved for moles of NaOH and then know that molarity equals moles divided by liters and solve for the volume after that. But we could also just use that as a conversion factor. So moles of NaOH cancels, and that gets us into the milliliters of NaOH solution that we would have to add. So we can use molarity as a conversion factor in both ways, to go from volume into number of moles, which we do at the beginning, and at the end, once we know the number of moles of NaOH, we can use the inverse of the molarity, divide by the molarity, to get back into volume of solution. And so with that set of unit conversions, what we get is 247 milliliters of our NaOH solution. Okay? So this was just basically a stoichiometry problem, but we're instead of finding the mass of a product or the mass of a reactant, we're finding the volume of the aqueous solution that we'd have to use to do this type of reaction. So questions about that one? Now another type of titration problem that's very common is to determine an unknown concentration. This is what I said we often do experimentally in the lab. So let's say we have, and this is the way, if we have a sodium hydroxide solution, how do we find out what its molarity is? This is what this problem teaches how to do. So we use a solid acid KHP with 1 acidic proton, and we have the molar mass of it here. And if we use 1.25 grams of that acid and it requires 56.3 milliliters of NaOH solution to reach the endpoint, what is the concentration of NaOH solution? So here what we're looking for is a molarity. Just like before, we should try to write out a balanced equation, or at least some semblance of a balanced equation, because we need to know the mole ratios of the acid and base and how they react with each other. So we have KHP. We don't have the full formula for that, but we know from the information in the problem it's a solid acid with 1 acidic proton, so it has 1 H plus. And then we react that with NaOH, which has 1 OH minus. So because there's 1 H plus, 1 OH minus, they react in a 1-to-1 ratio, so we don't have to have any coefficients to balance the reactant side. If we care about the products, which we don't, there would be some sort of ionic compound, some salt of whatever the KHP anion is, but we don't have the information about that, and then you would make water. But again, the important part is that these react in a 1-to-1 ratio, so there are no coefficients needed in this case because it's a monoprotic acid, an acid that has one H plus reacting with NaOH, which has one OH minus, so they react 1-to-1. So that's the equation. Now what we should also think about at the beginning of the problem is what are we looking for here to help us figure out what information we need. So we're looking for the molarity of the NaOH solution. And remember from the definition of molarity, there's two things that we need to find molarity. We need the moles of the solute, NaOH, and we need the liters of the NaOH solution. So that's the two pieces of information we need. If we look at the information in the problem, we know that we're using 56.3, oh no, it must not have charged properly today. If someone has one, that would be amazing. So the hero will reveal himself very soon. We'll talk about that later. All right. All right, I think we're avoided disaster, so thank you very much for that. All right, back to where we were. We want to find moles and liters. We already have the volume of solution in milliliters, so this denominator part here we kind of already have in the problem. It's given to us. We know what volume of NaOH solution we're using. We just have to convert that into the correct unit. But we have to use stoichiometry then to find the moles of NaOH that are taking part in this reaction here. So from that, it's again a stoichiometry problem. So we do moles of NaOH is what we're looking for. In this case, we know the mass of the acid we're using and the molar mass. So we're going to use mass and molar mass to get moles of acid. We have 1.25 grams of KHP. And then we have the molar mass, so 1 mole of KHP has a mass of 204.22 grams. So that converts into moles of acid, and then we use mole ratios to convert into moles of NaOH, our base, which is just 1-to-1 in this case. 1 mole of NaOH reacting with every 1 mole of acid at KHP. And that gives us 0.00612 moles of NaOH. So we use the titration data, the amount of acid that we use, to figure out how many moles of base that would have to react with. And so now we know the moles of NaOH. We have to find the liters of NaOH solution to be able to put it in the denominator here. And that's just a simple unit conversion. So again, the problem tells us that we're using 56.3 milliliters of our NaOH solution to reach the end point. And the corresponding volume in liters, we just have to divide by 1,000. So 1 liter has a volume of 1,000 milliliters. Those are equivalent quantities. And so then the volume of this is going to be 0.0563 milliliters. You should be able to probably divide by 1,000 in your head for the most part. And then finally what we have to do is just divide the two. So the molarity of the solution is just the moles, which we found from the stoichiometry, 0.00612, divided by the volume, which we just converted into liters, which I messed up because I'm still flustered about my battery almost running out, 0.0563 liters, and that gives us then a molarity of 0.109 molar. Okay? So when you're finding an unknown concentration, you need moles and you need liters. Usually the volume of solution that you're using is going to be given to you in the problem, and then you have to use the titration data and the stoichiometry to find the moles. Okay? Yeah, we're going slow today. All right. Next thing is any questions on that? All right, next one is just a slight variation of this. I think I gave us an extra slide to do more work, but we didn't need it. So let's move on to this one here, which is about acetic acid. So the slide that I skipped is the same thing, just more space for work if we needed it. So nothing new there. Here we have the similar situation. This time we're looking for the concentration of the acid instead of the base, but it's the same concept. The only difference here is that instead of using a solid as one of our reactants where we know the mass of that reactant, here we're just using two solutions where, again, it's volume and molarity that we're going to use for both to tell us the amount. So it's a variation on the same theme here. So we're looking for the concentration of the acetic acid solution. So we're looking for molarity of acetic acid, which is CH3COOH, or HC2H3O2 is another way to write that. And so we're looking for the moles of the acid and the liters of that solution that we're using. Just like before, we know that we're using 100 milliliters, which is the volume of our acid solution. So we already have this part of the equation, which in liters is 0.1. So we have the volume, we just again have to find the number of moles using the titration data that we have. So we need a balanced chemical equation to know if our acid and base react in a 1-to-1 or 1-to-2 or whatever ratio. We have to remember that acetic acid only has one acidic proton. Just the hydrogen that's bonded to oxygen is acidic. That's the only one that would react with a base. So it's one acidic proton. Again, we have NaOH, which has one OH minus. So these two will also react in a 1-to-1 ratio. Anytime you have one H plus in your acid and one OH minus in your base, they react 1-to-1. Then the products of this, which again don't matter for a titration problem, are going to be the salt that you form from the acid, which is CH3COO minus. So sodium cation paired with the anion acetate, and then water. But as long as we know that the acid and base react in a 1-to-1 ratio, that's all we need for this problem. So we now have that information, and we can find then using stoichiometry the moles of acid that are involved in this reaction. So we know the volume and molarity of the base that we're adding, and so we can use that information and the chemical equation to tell us how many moles of acid were present in that unknown solution. So we have 53.24 milliliters of our NaOH solution. That's the one where we know the volume and the molarity, so that's what we start with. We know the molarity of that is 0.125, which is 0.125 moles of sodium hydroxide per 1,000 milliliters, or 1 liter. In this case, milliliters is more convenient because that's the volume we started with. So we have moles of NaOH. We use the balanced chemical equation to convert moles of NaOH into moles of acetic acid. So 1 mole of acetic acid per 1 mole of NaOH. And that gives us what we want, which is moles of acetic acid. 0.00666 moles. Alright, I didn't do that on purpose. It's just a number, nothing to be afraid of. Alright, and then when we're going to find the molarity, we take the moles of acetic acid and we divide it by the volume of the solution, which we already have from the problem. So that's what we're going to do. We're going to have the 0.00, and these sixes aren't going anywhere anytime soon because we're going to divide that by the volume, which is 0.1. So it's still going to be the same thing. Just move the decimal place 1. So moles divided by the volume gives us molarity, which ends up being 0.0666 molar. Okay? So same concept as before. The only difference was in this case we're starting with a volume and a molarity of an aqueous solution, and we're using that information to give us the moles of the acid or the base that we used. So two variations on the same theme, and a very common type of titration problem involves finding unknown molarities where you need the moles and the volume, the moles and the liters. Okay? And we can just keep doing more of these because they're good fun. So let's talk about another type of titration problem, which is determining an unknown molar mass. So I hinted earlier in the course that there would be a lot of problems in this course that require us to find unknown atomic or molar masses, and this is one type of those. So here we have, and this is actually a lab that I was a lab experiment that I was a TA for when I was in graduate school. I don't think they do it here, but if you have an unknown amino acid which has one acidic proton, so it's HX, just one acidic proton, and we dissolve it in water. We have 0.254 grams of that, and we titrate it with 0.125 molar NaOH solution, and we find that 27.1 milliliters of that solution are required to reach the equivalence point, or the end point. We want to know what is the molar mass of the unknown amino acid. All right, so if you know, you can use titrations in this case to figure out what an unknown molar mass is, or something you don't know the formula of or anything about it. We just use titrations to help us do that. So what we have to think about here when we're doing problems that require us to find unknown atomic or molar masses, either for elements or compounds, remember that there's two pieces of information we need to find the molar mass. So the molar mass, or molecular weight, of our unknown acid HX is given by the mass of that. So remember that the definition of molar mass is the number of grams in 1 mole. So if you have the ratio of the two, the grams of the HX that you use and the equivalent quantity of moles, and you divide the two, that will give you the molar mass in grams per mole. So anytime you're finding a molar mass, you need the mass and you need the number of moles, and then you divide the two. The ratio gives you what the molar mass is, the mass of 1 mole. In this problem, the numerator, the mass of HX is given to us. We're told, and this is what we would, in the lab, we would weigh this out ourselves, that we're using 0.254 grams of our unknown amino acid. So we know the mass. All we have to do again is use titration information to find the number of moles and then divide the two. Okay? So the moles of HX we use, again, starting with the volume and molarity of the solution that we know. So we know that we have 27.1 milliliters of NaOH solution. We know the concentration is 0.125 molar. We also know that they react in a 1-to-1 ratio. I guess I haven't said that yet, but just like the previous problems, it's HX with one acidic proton, and so it will react with NaOH in a 1-to-1 ratio. So same story as before, different acid, but still one acidic proton, so they react 1-to-1. The products, which we don't care about, are sodium, whatever X is, the anion, and water. But it's this part here that we need, the 1-to-1 ratio between the two. And with that information and with the volume and molarity of the base that we're using, we can figure out the moles of HX that were in that sample. So we have 27.1 milliliters of NaOH solution. We have the volume of our base. We have the molarity of our base, so we can find moles of NaOH. Same molarity as before, 0.125 moles of NaOH per 1,000 milliliters of solution. So that's moles of NaOH, and then because it's a monoprotic acid with one H+, they react in a 1-to-1 ratio. So for every mole of NaOH, we also have 1 mole of HX. So the ratio again is just 1-to-1. And this gives us then 0.00339 moles. So that's going to be the denominator of this ratio. And so now we just need to divide the two. The molar mass of HX is the mass that we're given, 0.254 grams. That's the amount of acid, again, that we used. .254 grams divided by the moles, which we just found, 0.00339. And that gives us a molar mass of 74.9 grams per mole. Now, of course, that information by itself doesn't allow us to identify the unknown amino acid, because this is a molar mass, which could be any combination of atomic masses, but it's a piece of the puzzle. So when you're determining the identity of an unknown compound, determining the molar mass can be part of that, and this is one way you can do this if your unknown compound is an acid of some sort. Okay, so we use titration to find unknown molar masses. Any questions on that? Alright, the last titration problem we'll do before finishing Chapter 6 is going to be about what's called a redox titration. So as I said, most titrations are acid-base titrations, but you can also do titrations that involve redox reactions, especially if one of the reactants or products changes color a lot when it undergoes the redox transformation. So the one we're going to do here is if you ever use hair bleach. So back when I was your age, frosted tips were very popular. I never had them, but they were very popular back in those days. Maybe they still are today. And so the active ingredient in those is hydrogen peroxide, or in some types of hair bleach is hydrogen peroxide, H2O2. So let's say we're going to determine the mass percent of the sodium hydroxide in our hair bleach, which has a bunch of other things mixed with it. So let's say we took 14.8 grams of hair bleach, and we titrated that with a KMNO4 solution. And I'm giving you the equation down here. For redox reactions, we wouldn't expect you to be able to come up with the reaction yourself. There's no way to easily predict that that's the outcome of this reaction. But what happens is the KMNO4 reacts with H2O2. You make oxygen, manganese 2, and water. This type of reaction would work because if you're curious, how do we know when we get to the end point? KMNO4 is very highly colored. It's like a purple or pink solution. And then the product Mn2+ is colorless. So as the KMNO4 reacts and converts to Mn2+, the solution will be colorless. And then once you've added enough of this so that this is in slight excess, the solution will look pink. So same story. In this case, one of the reactants also serves as the indicator. That's just a side story. But the point is we want to know what is the mass percent of this hair bleach in terms of H2O2. So we're using 43.2 milliliters of KMNO4 to reach the end point. And we want to know what is the mass percent of H2O2 in the hair bleach. All right, so it's also often helpful to think about what quantities we need to solve the question that we're asking about. So we want mass percent of H2O2. So remember, mass percent, not a very common unit for solutions, but we can use it. It's just the mass of whatever solute we have divided by the mass of the solution, which in this case is hair bleach. And then that ratio times 100. All right, so in this case, what we're looking for is the mass of H2O2 that's present in that sample. We know that the mass of solution that we're using is 14.8 grams, so we already have the denominator of that ratio. But we need to use the titration information to figure out what mass of H2O2 is present in that solution, based on, again, how much of the titrant we use, how much of the KMNO4 we use to titrate it. So that's going to be, again, a series of conversions that start with the molarity and the volume of whatever we're using to titrate. So we have 43.2 milliliters of KMNO4. So that's the volume of KMNO4 solution. We know that the molarity of that is 0.105, so we can find moles of KMNO4 using the molarity. So even though it's not obvious what path we're going to take to solve this just yet, convert into moles is always a good thing to do. Now, one thing that I hope doesn't throw us off too much is we notice that this reaction, the chemical equation is written in ionic form as a net ionic equation. So we don't have potassium permanganate, we just have the permanganate anion present. So even though this is a trivial conversion, what we should recognize is that 1 mole of KMNO4 has 1 mole of MnO4 minus, which is the reactant that we have in our equation. This step is sort of optional. You just have to recognize that when we dissolve potassium permanganate in water, it's a 1-to-1 ionic compound, 1K plus, 1 MnO4 minus. So when we dissolve that, we get 1 mole of KMNO4. As I said, this step is optional as long as you can recognize, because in the equation, the reactant is written as just the anion, MnO4 minus. So that's a trivial step, but I just don't want to have to throw anybody off and not do any alchemy and convert one substance into another without any justification for that. And then what we have to use is mole ratios to figure out how many moles of H2O2 are in there. So we've converted into moles of MnO4 minus. We have coefficients in the balanced chemical equation that allow us to figure out how many moles of H2O2 would react with that. So the ratio is a little bit more complex this time. It's 5 to 2, but we just use coefficients. A coefficient of 5 for H2O2 and a coefficient of 2 for MnO4 minus. So that converts moles of MnO4 minus into moles of hydrogen peroxide. What we're looking for is the mass of hydrogen peroxide, but once we have moles, we know we can use molar mass to find the grams. So we have moles, we use this molar mass of 34.02, which is grams of hydrogen peroxide, H2O2, per 1 mole. And so if I did all the numbers correctly, we get 0.386 grams of hydrogen peroxide. We put that back up into here to calculate mass percent. That's the numerator of this mass ratio. And what that comes out to is 2.61%. So a relatively small percentage of H2O2, which is the active ingredient in hair bleaching. Okay? So it's a lot of, there's a lot of different variations on titration problems, a lot of different things we can ask you to do, but a lot of the key steps are always the same. We're using molarities and volumes to find moles of one reactant. We're using mole ratios to find the moles of the second reactant, and then that in some way is going to help us determine whatever it is we're trying to find about that reactant, whether it be its molarity, its molar mass, its mass percent, a lot of different possibilities there, but you just have to think about what the problem is asking you for and then use a series of conversions to get the information you need. All right, I think this is the end. Yes, this is the end of Chapter 6. So this is the end of Midterm 2 material, in case there's anything unclear about that. So everything I've covered up until now is fair game for the midterm that happens next week. While I'm on the topic, the final reminder about the exam review session, which will be Friday at 1 p.m. in here. So if you want to come to that, we'll go over everything from chapters 4, 5, and 6, or at least as much as we can to help prepare for the exam. We're going to now move on to chapter 7, which won't be on the next exam, but of course will be covered on the third exam and the final. So any last wrap-up questions on chapter 6 before I jump forward to the next chapter? Yep. 1, 2, yeah. Yep. It's 100, right? Oh, this conversion here? So this is just another way of writing molarity. So molarity is moles per liter, and a shortcut would be just write it as moles per 1,000 milliliters because we're starting with milliliters of solution. So we could have done this as two conversions. We could have converted milliliters to liters and then multiplied by molarity, or we can just write that as a combined. I like to use that shortcut because it saves a step. It's just rewriting the denominator, instead of writing it as 1 liter, writing it as 1,000 milliliters. Sorry, and your question over here was about this one? Okay, got it though? All right, good. Okay, so let's move on then to chapter 7 if there's nothing else. All right, so chapter 7 is all about energy. It's called, or what we call thermochemistry, which is energy changes in chemical reactions. We did get a brief introduction to this topic in chapter 3. We talked about how we could use bond energies to determine the change in energy for a chemical reaction. So this is going to be a lot more things related to that, chemical energy, internal energy, and changes in those energies as we do chemical reactions. What we're going to start with is a pretty physics-based definition of energy before we work into how this relates more closely to chemistry. So let's get some basic definitions down. A lot of this was covered in the review chapter, but I'll go over it briefly since we haven't really seen it yet. So energy, the simplest definition of energy is the capacity to do work. We'll define work in a little bit more detail here in a second. But energy has two different forms, and an important concept about energy is that we have what's called the law of conservation of energy, which means that the energy of the universe is constant. And energy can change forms from one form to another, but you're not going to ever create or destroy energy. And so energy has two different forms. It has kinetic energy and potential energy. So those are the two possible forms of energy. Now there are different subcategories within each of these. So kinetic energy is energy due to motion. So anything that's moving has kinetic energy associated with it. And if you take physics, you'll learn how to calculate that. And then potential energy is energy due to position or composition. And so the type of energy we talk about primarily in chemistry, which is the potential energy of chemical bonds, is a form of potential energy. So when we talk about how bonds store energy, and when you break bonds and form bonds, you have delta E that we calculated back in Chapter 3. That's really changing potential energy. Kinetic energy is not terribly important for chemistry because the potential energy, the energy that's stored in the chemical bonds, is much larger than any energy that's associated with the motions of the atoms. And really, since mass is conserved during a chemical reaction, typically the kinetic energy is conserved anyway. So we don't really care about kinetic energy for a chemistry standpoint, but we should be aware that energy has two forms, kinetic energy and potential energy. And whenever we're defining a change in energy for something, we have to define what's called the system and what's called the surroundings. So the system is the part of the universe that we're studying, or the part of the universe that we're focusing on. Whenever we're measuring a change in energy. All right, so the system is the part of the universe we're focusing on, which, if you're doing a physics experiment, it could be whatever object you're dropping from the ceiling, or whatever object is moving across the floor that you're trying to measure. It's just whatever part of the universe that you're focusing on and measuring. And in the context of chemistry, though, what do we usually define as the system in a chemistry standpoint? The system is usually a closed container of a substance or a chemical reaction. So we'll talk about aspects of energy related to just physical processes, which is substances basically changing their temperature or other properties of those, or also chemical processes, which are chemical reactions. So the system in a chemistry standpoint is usually just the substance that we're measuring, or it could be the whole chemical reaction, the reactants and the products that are involved in that chemical reaction. So that's how we define system, and then surroundings is everything else that's not part of the system. The whole rest of the universe is considered the surroundings. Okay, and when we have an energy change for our system, it's not, again, that we're creating or losing energy, it's that energy is being transferred between the system and the surroundings. So if the energy of the system goes up, that means energy from the surroundings is being put into the system. If the energy of the system goes down, it means that energy is being lost to the surroundings. So that's kind of the idea of conservation of energy and how the system and the surroundings are related to each other. So what we want to talk about next is the two ways that we can change the internal energy of our system, and the two different forms of energy transfer, which are called heat and work. So whenever we're changing energy, which is delta E, it's the final energy of the system minus its initial energy. So anytime you see capital Greek letter delta, that refers to final minus initial. But then, what are the two ways by which we can change that internal energy? One of those is by adding or subtracting heat from the system, and the other one is by doing work or having the system do work. So heat and work are the two ways that we can change the energy of our system. So another terminology for heat is thermal energy. So those are used interchangeably. And this is energy that's transferred due to temperature differences. Alright, so whenever your system and your surroundings have two different temperatures, you will have heat transfer between them. And this, I think, we know intuitively. If you take an ice cube and put it into a glass of water, the temperature of the whole thing goes down because there's heat transfer between the water and the ice cube. Or if you put something that's boiling hot into a cold glass of water, the temperatures of the two things will change as heat is transferred between them. So anytime there's a temperature difference between system and surroundings, two things that are in contact with each other, heat will be transferred. That's one form of energy transfer between the system and the surroundings. And then the other one is work, which in a generic sense is all other forms of energy transfer are categorized as work. And typically this refers to a situation when an object is being moved by a force. So it's a force over a distance, as you probably know from physics class if you've taken that. And so when an object is being moved by a force, we call that work. And this is the other way that we can change the energy of our system, is by the surroundings doing work on the system or by the system doing work on the surroundings. So these are the two ways that we can have a non-zero delta E, is by putting heat into the system or taking heat out of the system, or putting work into the system or taking work out. Okay, so those are the two forms. And so what we have then is that the delta E, the change in energy, is just the sum of heat and work. So Q is the abbreviation we use for heat, W we use for work, obviously. And so the sum of heat plus work gives us what the delta E is. So if we know both of those processes and how much of each is occurring, we can calculate delta E for our system. Now, one thing we want to be aware of when we're talking about heat and work are what are the sign conventions for heat and work. They can be positive or negative. And so whenever the system absorbs heat, in other words, when the system has its temperature increasing by heat being transferred from the surroundings, that's going to be a positive heat term. So Q is going to be positive whenever heat is absorbed. And then work will be positive whenever work is done on the system. Okay, so if we're putting a force into the system, doing work on that system, the work term will be positive. And so anytime when Q and W are both positive, if you add two positive numbers together, you know for a fact that delta E is also going to be positive. Okay? The internal energy will increase in that case. So whenever delta E is positive, that means the internal energy of your system increases. The other possibility is the opposite of that. And so if we have heat released by the system, so if our system is at a higher temperature than the surroundings, it will release heat to the surroundings. In that case, the Q term would be negative. And then the opposite for work would be if the system is doing work. So if work is done by the system, that would also be negative. And so if both Q and W are negative, that would mean no matter what those values are, the delta E would have to be negative as well. The sum of two negative numbers is always a negative number. And so in this situation, the internal energy decreases. But then we also have the possibility where heat and work are taking place as on the system, being added to or taken from the system, where the signs are opposite. So if we have the situation where the system absorbs heat, so that means Q is positive, but at the same time the system does work. Work is done by the system, which means the W term is negative. The sign of delta E depends on the magnitude of Q and W. So one's positive, one's negative. When you add the two together, whichever one's higher magnitude is going to determine what the sign of delta E is. Okay, so this will depend on, the sign in this case will depend on the magnitude of Q and W. And then the opposite possibility is, of course, true, is likely as well, or possible as well. So if you have work done on the system, a positive work term, but at the same time you have heat released from the system, so your Q is negative. If one term is positive and one term is negative, the sign of delta E will again depend on the relative magnitudes of the two. So these are the four possible outcomes when you have heat and work going into a system or out of a system depends on the magnitude of Q and W when the signs are opposite. But what we really want to understand on this slide is the difference between a positive heat, which is heat absorbed by the system, a negative heat, which is heat released by the system, and then positive and negative work. Work being done on the system or by the system, respectively. Okay, so that's what we really want to take home from this slide is the sign conventions we use. We'll talk in a little bit future how to calculate Q and W separately. We'll do a little bit of that today with W at least. Now the next thing we want to understand about delta E, change in energy, is what's referred to as a state function, path independence. Alright, now, so certain parameters of our system are defined as what are called state functions, and a quick way to identify a state function for our purposes is anything with a delta in front of it. So anything that uses that Greek letter delta to indicate a change, whether it be a change in energy or a change in something else that we'll get to later. Oh, sorry, just delta, not delta H yet. A state function is anything with delta in front of it we can quickly identify that as a state function. So delta E would be a state function. And so what does that mean then about the properties of delta E? What is the definition of a state function? A state function is any function like delta E that only depends on the final and the initial states. It doesn't matter how we got between the two. And that's what we mean by path independent. So let's say we have this situation illustrated down here where our initial state has an energy of 10 joules. Usually we can't measure absolute energies, but let's pretend that we can here. So we have an initial state that has an energy of 10 joules and a final state that has an energy of 20 joules. The delta E for this will be 20 joules, which is our final energy, minus 10 joules, which is initial, which is plus 10 joules. And it doesn't matter how we got between the initial and final state, what path we took to get there, delta E will always be plus 10 joules. So to illustrate that further and to contrast a state function from something that's not a state function, let's think about two possible ways we can get there. We said in the last slide that delta E is the sum of Q plus W. So let's say we did this path to get between the initial and final state. Let's say we first did 30 joules of work on the system. So if we do 30 joules of work on the system, our energy is going to temporarily reside at 40 joules. But then from there, if we released, I didn't draw that line very well. If we release 20 joules of heat, our delta E would be Q plus W, which is still plus 10 joules. So this is one path we could take to have this overall energy change of 10 joules. We could add 30 joules of work, remove 20 joules of heat, but we could take another path to get there. We could do, these are just randomly chosen, and I'm not saying that there's anything important about these numbers that I'm picking here. But let's say we released 20 joules of heat first. That would take us to a state that has an energy of minus 10 joules. And then let's say we did, as a second step, we added 30 joules of work. We did work on the system. Delta E is again Q plus W, which still equals plus 10 joules. So the heat and the work terms could be any combination of numbers that add up to be plus 10 joules. So heat and work are not state functions because the value of Q and W depend on the path that we take to get between our initial and final state. So just by knowing that our initial state has an energy of 10 joules and our final state has an energy of 20 joules, we cannot calculate Q and W from that information. We can only calculate delta E. So delta E only depends on the initial and final state, not how we got there, but the values of Q and W will depend on what processes we took in the course of going between our initial and final states. So that's hopefully a little bit of an explanation about the difference between state functions and what path independence means. So any questions on that? That's kind of conceptual. It's not going to be something that comes up a lot, but we do want to know at least the definition of a state function. So anything you want me to clarify? So the only calculation we're going to learn how to do today is the only type of work we're going to deal with, which is called expansion work. Work is another one of those things that's not terribly important in chemistry. We don't usually have chemical reactions that do a lot of work for us, but they can do in some cases. or at least the energy that's released from a chemical reaction can be converted to work. Really, the only type of direct work calculation we're going to do is what's called expansion work. So expansion work is when you have a sample of a gas, and then that gas, the volume either expands or contracts. The volume gets bigger or the volume gets smaller. That's what and there's going to be work that's associated with that process. Now, we're going to talk more about gases in the next chapter, so some of these things will make more sense after Chapter 8. For those two are on the same exam, so that's helpful. But let's just talk a little bit about expansion work for now. So expansion work is given as the negative of the external pressure times the change in volume. All right, so let's define pressure real quick. Pressure is force divided by area. So as we'll deal with in a lot more detail in Chapter 8, when you have a sample of a gas, the molecules or the atoms are moving around really fast, and so they exert a force on whatever container is holding them. And so pressure is that force divided by whatever area they're pushing against. And so and the external pressure, P external, is the external pressure. So it's whatever pressure is basically pushing down on the sample of gas in reality. So P external is a constant external pressure. So this equation only works when the external pressure is constant. There would be other equations for expansion work that apply when you're doing other types of expansions if the external pressure is not constant, for example. You'll talk about those in physical chemistry, but not in this class. So this is the only one we're worrying about is external pressure is constant. The equation is minus P external delta V. Delta V is the change in volume. So as the gas expands or contracts, its volume changes, and that also goes into the calculation of whatever work is involved with that process. Now, the only weird thing about this equation, it's a very simple equation. You're just multiplying two things together, a pressure and a change in a volume. Usually very easy to calculate. We just have to be a little bit careful with units on this because the standard unit for pressure that we'll use is what's called atmospheres, which is it's basically the air pressure at sea level. And it's defined as 1 atmosphere. And then the volume change that we're going to do is going to be in liters. So the work term that we calculate is in liter atmospheres, but the standard unit for work is going to be joules, so we have to do a conversion usually. So what we have to remember is that 1 liter atmosphere is 101.3 joules. Okay, so that's a new conversion we haven't seen yet. And the origin of that number will become more clear in the next couple of chapters. But 1 liter atmosphere is 101.3 joules, so we have to keep that in mind. And then the signs, let's think about the signs of our work for a second. So if our final volume is larger than our initial volume, which means the gas expands. Now in this case, this equation is defined with the sample of gas as our system, so that's the part we're focusing on. So if the gas expands, its change in volume is greater than 0. And from this equation, that means the work term is negative. And that, as we said before, means that work is done by the system. So whenever a gas expands, the sign of the W, the sign of the work, is going to be negative. And in the opposite situation, if we're compressing the gas, V final is smaller than the initial, which means we're compressing the gas to a smaller volume. Delta V is less than 0, which means the work is going to be positive, greater than 0, because of this minus sign out in front of that equation. All right, so if the gas compresses, it's positive work, which means that work is done on the system. And this would hopefully make a little bit of intuitive sense. If you have a sample of a gas and you want to compress it to a smaller volume, you have to put a force onto it. You have to do some work on that gas to get it to go to a smaller volume, if you've ever thought about it that way. Okay? So that's expansion work, the only type of work that we're going to be worried about in this class. And so let's just do one example problem of this. So let's say we have a reaction that produces a gas, and the volume expands from 1 liter to 10 liters against a constant pressure of 0.978 atmospheres. Calculate the work done. So the problems don't get much more complicated than this. We're just calculating work. We have the external pressure and we have the change in volume. Those are the only two terms we need. So work is just going to be the negative of the external pressure times change in volume. And we're told that the external pressure is 0.978 atmospheres. So negative 0.978 atmospheres is that's the external pressure, and then our change in volume. Remember, anytime we have delta, that means final minus initial. Our final volume is 10 liters, that's what we end up at. Our initial volume is 1 liter. So our change in volume is 9 liters. So we multiply the external pressure, the negative of it, by that. And so we get a work of minus 8.80 liter atmospheres. Again, keep close track of your units on these. So pressure in atmospheres, volume in liters. So the work term is given in liter atmospheres. I didn't specify it here, but typically we want to convert that into joules. So the work in joules would be that number minus 8.80 times the conversion factor that we just introduced, which is 101.3 joules per liter atmosphere. Or minus 891 joules. Okay? So the work is negative because the gas is expanding, as we just talked about, and this is how you would calculate it. And really the problems don't get much more complicated than that. Keep in mind, if the external pressure is 0, if the gas is expanding against a vacuum, then the work would be 0. But really the calculations don't get any more complex. Alright, the last thing we want to introduce today, let's see if we have time for this. We might get through some of this at least, is enthalpy. Alright, so enthalpy is another term that we often use in chemistry. So, what is that? That'll work here. Okay, so let's introduce enthalpy here for a second. So the issue with chemical reactions is that most things that we do in a lab are at constant pressure. So if you have a reaction having a constant pressure, if we wanted to calculate the energy change for that reaction, we would have to calculate the heat and the work, because at constant pressure there's going to potentially be expansion of the system, as we saw, and you'd have to worry about work Q and W. So delta E is equal to Q plus W. And what we want to do is derive a new state function that doesn't require us to determine Q and W separately. We want to derive a simpler one, which we call enthalpy. And so the work in a constant pressure setting is given as minus P external delta V, as we just saw, which we can rewrite more simply as minus P delta V. So if the pressure is constant, we can use this as our equation for work. And then if the heat is measured at constant pressure, we can abbreviate that as QP, the little subscript P telling us that we're measuring heat at a constant pressure. Remember, heat is not a state function, so whether you're doing the process at constant pressure or not would potentially change the value of Q. So we specify that heat is measured at constant pressure, and so we can rewrite this equation as delta E at constant pressure is going to be QP minus P delta V whenever we're at a constant pressure. And then what we want to do is we're going to solve for QP. So if we can just measure the heat of our reaction, of our system, the heat that's either put into or taken out of the system, that's a little bit simpler than measuring heat and work separately. So we get QP is equal to delta E plus P delta V. So we're just rearranging this equation, solving for QP. And then what we call this is delta H. So that's this new state function, enthalpy, where delta H is equal to the heat measured at constant pressure. And that's why it's a convenient unit for us, is because we can just measure the heat and we get our change in enthalpy directly. Alright, so H is what's referred to as enthalpy. Which is equal to E plus PV. And because, I guess one thing I should have pointed out is because delta E and delta V are both state functions, the sum of two state functions gives us another state function. So enthalpy is also a state function. It only depends on the initial and final states, and it's why it has a delta in front of it, as we said. And so this delta H is a new state function. equal to the heat measured at constant pressure. Alright, and so then the last thing we'll talk about today, we'll put off the last couple slides until next time, is the relationship between delta H and delta E. I'll show you if you'll find. Alright, so comparing delta H and delta E, as we said, delta H is equal to delta E plus P delta V. And so you might be thinking, well, what's the point of measuring enthalpy change delta H? Isn't delta E what we're actually interested in, the change in energy? And what this slide will hopefully convince you is that delta H and delta E are usually very similar to each other. It's just that delta H is more convenient to measure directly. So let's say that we have reactions that don't involve gases. Typically these are going to involve very small volume changes. Okay? So if our reactants are all liquids or solids, or solutions of those, when you do a chemical reaction in a condensed phase, in a solid or a liquid phase, you don't change the volume very much. That means that this P delta V term is very close to zero, this term here, and that means delta H is pretty much identical to delta E. So for most chemical reactions, especially those that we do in solution, like we just talked about in Chapter 6, delta H and delta E are pretty much the same in terms of their quantity. Now let's say we have a reaction that involves a gas, but the moles of gas does not change. So as an example, we have hydrogen and chlorine reacting, both gases, to make 2 moles of HCl. What we see is that we have 2 moles of gas on the reactant side, we have 2 moles of gas on the product side. Now something that will become more clear in the next chapter is that whenever the moles of gas is not changing in a chemical reaction, this P delta V term is equal to 0 rigorously, which means this is another situation where delta H and delta E are equivalent. Now there's one final possible scenario, which is where you have a reaction that either produces gas or that in net consumes the gas. So if we take carbon monoxide and we oxidize it with O2 to make carbon dioxide, what we'll notice here is that we have 3 moles of gas as reactants. 2CO plus O2 is 3 moles of gas total. And then as a product, we're only forming 2 moles of gas. So in that, we're consuming gas equivalents in this reaction. And so P delta V in this case would not be equal to 0, which means delta H would not be equal to delta E, rigorously speaking, because this term is no longer non-zero whenever the moles of gas are changing. But in reality, this P delta V term is usually much smaller than the QP, the heat that's involved from this reaction, which means even for these situations, delta H and delta E are not all that different from each other. So this is just giving you the relationship between those two state functions and convincing you that delta H is very commonly used in chemistry, but it means roughly the same thing as delta E, and it has roughly the same value. In chemistry, you'll learn more specifically about the relationship and the quantitative differences between these. We'll put off the last 2 slides until next time, and as a reminder, we'll have the review on Friday and the exam starting on Monday.